All right, let's look at two counting problems involving bridge. So bridge is a game of cards that you play with a deck of 52. Everybody gets 13 cards. 4 people play, everybody gets 13 cards. So problem 1. In bridge, 4 players each get 13 cards. So that's the whole deck. The question is, what is the probability that one player gets all 13 spades? So that is the probability that the 13 cards that one player has is all 13 spades. So I thought of 3 ways to answer this. I got this problem from the book. Ross thought of 3 ways to answer it too. And the 2 of us have 1 way in common. So that means that there's a total of 5 ways to do it. I'll show you my 3 ways, and then if you want, you can look in the book and see the other 2 ways that he thought of that are different. So my first answer, all the answers are going to be the same, but the ways of looking at it are different. So I say that there's 4 times 13 factorial times 52 minus 13 factorial all over 52 factorial ways. So the approach I'm using here is I'm looking at everything as ordered. So the 4 comes from deciding which of the 4 players gets the spades. And then I'm thinking of so let's say this is the spades player. I'm thinking of giving this player the 13 spades in order. So one of the 13 factorial possible orders. And we'll have a permutation of all 52 cards. The first 13 cards are going to be spades, and then the next 39 cards are going to be everything else. So 13 cards here, 39 to everybody else. So the 13 factorial is to give the spades in order to the player getting the spades. And then the 52 minus 13 factorial, or 39 factorial, is give others the cards in order. And then the 52 factorial is the total number of permutations of 52 cards. So there's 4 ways to choose which player gets a spade. So I could be giving spades here and then 39 cards there, or I could be giving spades here and then 39 cards, just permute the other 39 cards in these 39 positions, or I could give spades to the 3rd player and then permute the other 39 cards, the other 39 positions, etc. So there's 4 possibilities that all kind of look the same without the 4. We've got 13 factorial ways of putting the spades somewhere, and then 39 factorial ways of putting the other 39 cards in the other 39 blanks. So I wouldn't simplify this too much, except if we look closely, we'll see 52 factorial, 13 factorial, and 52 minus 13 factorial are all parts of 52 choose 13. So this is the reciprocal, because 52 choose 13 would be 52 factorial over 13 factorial times 52 minus 13 factorial. So this is 4 over 52 choose 13. It's not a terrible expression, but I think this is pretty nice. It's definitely very compact. Alright, so that's the first answer I get. Alright, for the second approach, let me do an unordered version of this. So my second answer is there's 13 choose, actually 4 times 13 choose 13 times 52 minus 13 choose 13, 13, 13. So it's a multinomial coefficient. Divided by 52 choose 13, 13, 13, 13. So there's this many ways, and now we'll do the unordered approach. So the 4 is the same. We'll choose who gets the spades. And then that player is going to get 13 cards, and of course we're going to give that player the 13, all 13 out of the 13 spades. Choose 13 is 1. So one way to do this. Then we'll take the other 39 cards and we'll give 13 to the second player, 13 to the third player, 13 to the fourth player. So we'll distribute the remaining cards. And then this 52 choose 13, 13, 13, 13 is the number of ways to take 52 things, put 13 of them on team 1, 13 of them on team 2, 13 of them on team 3, and 13 on team 4. In this case, the team is a player. We'll give 13 cards to person 1, 13 cards to person 2, etc. So we could say this is the number of bridge deals. Alright, so that's a perfectly good expression. Maybe the 13 choose 13 is unnecessary because it's just multiplying by 1. And normally I wouldn't bother simplifying it too much. Well, except I want to see that it's equal to the answer I got the first time. So let's see what we can simplify. We probably can simplify a lot because there's all these 13 factorials hanging around and they're going to cancel with each other. Alright, so this equals 4, I'll drop the 13, choose 13, which is 1. 52 minus 13 is 39 factorial over 13 factorial, 13 factorial, 13 factorial. Divided by 52 factorial over 13 factorial, 13 factorial, 13 factorial, 13 factorial. Alright, now an awful lot cancels. 3 of these 13 factorials cancel with 3 of those, leaving us with 4 on the top times 39 factorial times 13 factorial over 52 factorial. Now again, 52 choose 13 is 52 factorial over 13 factorial times 39 factorial. So this is 4 over 52 choose 13. So we can see that we get the same answer this way. Alright, now in case that isn't enough, here's a third way to think of it. And this approach is, I'd say, unordered, but using probability more than the first two did. The first two approaches, we didn't think about probability until all the way at the end, when we made our fraction. Number of interesting cases over total number of cases. So let's let AI be the event that player I gets the spades. All 13 of them. So we want the probability that player 1 gets all the spades, or player 2 gets all the spades, or player 3 gets all the spades, or player 4 gets all the spades. Now normally a union like this is a union of is a sum of the individual probabilities minus all the intersections of 2 at a time plus all the intersections of 3 at a time minus the intersection of all 4 at a time. But the intersections are they all have probability 0, because it's impossible that player 1 gets all the spades and player 2 gets all the spades. Once player 1 gets all the spades, that's all the spades and nobody else gets any. So this is just the probability that player 1 gets all the spades plus the probability that player 2 gets all the spades. We can just add these together. And there's nothing to subtract because the intersections are all empty. Oops, plus. Alright, so we conceivably have 4 things to compute here, except if you think about it, by the symmetry of the game, 4 people each getting 13 cards, my opinion that person A gets all the spades is exactly the same as my opinion that person 2 gets all the spades. And that's the same as my opinion that person 3 gets all the spades. Because naming them player 1, 2, 3, 4 is kind of arbitrary. Any one of them could be named player 1. So these have all got to be the same. So this is 4 times the probability of A1 by symmetry. And here, symmetry means considering things that are exactly the same except for their labels. Here the players are exactly the same except for their labels. Alright, so we really only need to consider the probability of A1, the probability that player 1 gets all of the spades. So the probability of A1 getting all the spades is number of bridge hands including all the spades over the total number of possible bridge hands. So there's only one bridge hand that includes all the spades. That's the 13 spades. And the total number of bridge hands is, well, there's 52 cards in a deck. We choose 13 of them to make a bridge hand. So that's 52, choose 13. And we wanted 4 times the probability that player 1 gets all the spades. So 4 times the probability of A1 equals 4 over 52, choose 13, which is exactly what we got the other 2 times. All right, now let's look at a second problem. Our second bridge problem. Again, 4 players are each going to get 13 cards. What's the probability that each player gets an ace? So it is, I should say, the point of view is going to be we'll have unordered hands for everybody. All right, so I'm going to give everybody an ace first. So if I have 4 aces and 4 players, I can distribute those 4 aces in 4 factorial ways. And then after I get rid of those 4 cards, there's 48 cards left out of 52. So I'm going to take the 48 and give 12 to one player, 12 to another player, 12 to a third player, 12 to the fourth player. So once I do that, that's all the possible bridge deals where everybody gets 1 ace. I want that over the total number of bridge deals, which is 52, choose 13, 13, 13, 13. So this 42, 48, choose 12, 12, 12, 12 is, we're distributing the other cards to the 4 players. Again, I'm not choosing the order for the cards in each player's hand. I'm just giving player 1 12 cards, player 2 12 cards, and letting each player order the cards in their hand exactly as they like. So I think this is a good expression, simplified enough. There is a lot that can cancel because we've got a bunch of 12 factorials and a bunch of 13 factorials, which are mostly going to cancel. So just to write this here, so I managed to write it as 13 to the 4th over 52, choose 4. Now that's a smaller expression, arguably simpler, but I can't think of a good way to interpret these numbers that makes us think about what's going on in the problem. I think this expression is more amenable to arrows and explanations for what all the pieces are. So I think I prefer this expression. The end.